Hello, in this video we're going to talk about acids and bases, and we're going to provide some definitions of these, and we're also going to look at how we can write chemical equations for the dissociation of acids and bases and how they react with water. And then we'll finish up this lecture looking at neutralization reactions, what happens when an acid reacts with a base, and how we can write that as total ionic and net ionic equations. All right. So let's talk about definition of acids. So there are a variety of definitions of acids, but one common one is that it's a substance that releases hydrogen ions, also known as H+ ions, when it's in an aqueous solution, so a solution that contains water. And sometimes it's called a proton also, because it just has like it has one proton and it has a positive charge. Now we can talk about what happens when an acid dissociates. So a common strong acid is hydrogen chloride gas, and when it dissolves in water, it forms what we call hydrochloric acid, and that's going to dissociate completely into protons and chloride ions. And because it dissociates completely, we call it a strong acid. If it only dissociates partially, we would call it a weaker acid. Now, one thing we need to keep in mind is that usually H+ ions aren't really existing in solution. They're attached to something else, and commonly that's water molecules. So HCl can donate its proton, its H+, its hydrogen ion, to a water molecule to form what's known as the hydronium ion, H3O+. And so this would be the description of that chemical equation. HCl plus water reacts to form H3O+ and Cl-. And this is a Lewis structure of the hydronium ion here. All right, so let's talk a little bit about bases. So they are the opposite of acids, and a base is any compound that can produce hydroxide in aqueous solutions. All right, and some properties of bases are they have a bitter taste, but don't try to taste a base because it can do bad things to you. Okay. And then it'll have a slippery feel if it's dissolved in water. And probably what that slippery feel is the base reacting with your skin. Okay. So another reason why to be careful with bases. And it turns red litmus paper blue. Okay. Some examples of bases. Strong bases are going to completely dissociate into hydroxide ions in solution. So some examples are group 1 or group 2 hydroxide. So these are group 1 and group 2 are the two leftmost columns of the periodic table. So potassium is in group 1, and that'll dissociate to K+ and hydroxide. Okay, calcium can also do this. So calcium hydroxide is the base. And you'll notice there's a little subscript 2 here. That means there's 2 hydroxides. Okay, so when this dissociates, we make the calcium 2+ ion. So if you remember, calcium likes to have a 2+ charge. And then we release 2 hydroxide ions. Okay. Now, what about ammonia, NH3? So this does not dissociate itself to make hydroxide, but it will react with water to make hydroxide. So it's a weak base even though it has no OH minus group. So let's look at that a little more closely. So ammonia will react with water in an acid-base reaction to make the ammonium cation and the hydroxide ion. So that's why it's a base, is we're making this in solution. Now this allows us to talk about another concept with acid-base theory. Okay, so one thing about this, you'll notice our reaction arrows are a little different. They're going in both directions. And that's to kind of signify that this reaction goes in both directions. It's an equilibrium reaction. Okay, and technically we might be able to say that every reaction goes in both directions, but a lot of reactions greatly favor the product side, whereas some reactions, they might favor the reactant side, the left-hand side, or you might have in favoring either side roughly equally. And when you get kind of close to it favoring either direction almost equally, we call that an equilibrium reaction. Okay. This also allows us to talk about conjugate acid-base pairs. Okay, so when ammonia, which is the base, reacts with water, the water is acting as an acid. Okay, and the ammonium is going to acquire a proton from the hydrogen, and we make what's called the conjugate acid of ammonia. And then we also make this, which is the conjugate base of water. So you can see that these acids bases and the conjugate acid kind of come in pairs. All right. All right, now, so we've kind of defined acids and we've defined bases, but we can also talk about how they will neutralize each other or react with each other, and we can give a chemical equation for that reaction. So when they react with each other, we call that a neutralization reaction. And in a neutralization reaction, hydrogen ions from the acid combine with hydroxide ions to form from the base to form water. And we also form what's called a salt, which is an ionic compound. Okay, so an example of this would be the reaction of the strong acid hydrobromic acid with the strong base sodium hydroxide. Okay, so here we have our acid and our base, and they react to form water and sodium bromide, which is our salt. Okay, so we can represent, so what we've shown here has been kind of like a total, a balanced chemical equation for the neutralization reaction. But we can represent this with what's called ionic equations. Okay, so here's another example acid-base reaction. This would be kind of the molecular equation. We're not really showing any of the ions. Now barium hydroxide, so hydroxides are often insoluble in water, but barium hydroxide is an exception to that. So here, to write a balanced chemical equation here, we have to have two HBr molecules reacting with every one barium hydroxide molecule. And that makes one molecule of barium bromide and two molecules of water. Okay. Now, we can also write this as what's called a total ionic equation. And so what you do to show a total ionic equation is that every molecule that's in the aqueous form, we're going to split it into ions, whereas molecules that either are in their solid form or their liquid form, like water here, we're going to keep kind of together. So HBr, when it dissociates into H plus and Br minus ions, so we need to kind of show them in that form. And so 2 Br molecules will split apart to make 2 H plus and 2 Br minus ions. We can do something similar with barium hydroxide. When it dissociates, we make 1 barium 2 plus ion and 2 hydroxide ions. We'll do the same thing on the right-hand side with the barium bromide. Okay, and that makes our total ionic equation. Now, what's kind of interesting here is at this point, you'll notice, so here's kind of my reactant ions and my product ions. There are some of these ions that appear on both sides of the equation. For instance, the 2Br ions, okay, and also the barium 2+ ions. And we call these spectator ions. And we call them spectator ions because they're not really participating in the net reaction because they're on both sides of the equation. So we can write what's called a net ionic equation, and that's where we kind of cross out the spectator ions and see what's left. And so if we do this with this equation, we get to a net ionic equation, which for this particular reaction is 2H plus 2OH minus going to form 2H2O. And you'll notice we've got all these twos here, so those we can divide both sides by 2, and we could also write this to simplify it as H plus OH minus going to form H2O. And that would be the net ionic equation for this neutralization reaction. And, okay, and that's going to conclude this video on acid-base chemistry. In our next video, we'll look a little bit more closely at how we can quantify how acidic a solution is. All right, thanks for watching.